First example of the situational problem. A long, narrow open container used to feed farm animals is filled with water, and its dimensions are 2 meters in length and a cross-section in the shape of an isosceles trapezoid, 30 centimeters wide at the bottom, 60 centimeters wide at the top, and height of 50 centimeters. If the container leaks water at the rate of 2,000 cubic centimeters per minute, how fast is the water level falling when the water is 20 centimeters deep? Let's start analyzing the problem. The dimensions of the container are given, including the cross-sectional area on the sides of the container, which are in the shape of isosceles trapezoid. Here's the clear picture of the parts of the container. We have the measurement for the bottom base of the trapezoid, which is 30 centimeters, upper base 60 centimeters, length of the container, which is 2 meters, and height of the trapezoid, or rather height of the container, which is 50 centimeters. The rate identified in the problem in cubic units per minute is about the container leaking water, which is an indication that the volume of the water inside the container is decreasing. This implies that the rate of change of the volume with respect to time t, dV over dt, is negative. The negative sign is used to represent the rate that is decreasing. So therefore, dV over dt is equal to negative 2,000 centimeter per minute. Then, in the latter part of the problem, we are asked to find the rate at which the water level is falling when the water is 20 centimeters deep. So let's say we use H to represent water level. Then we are looking for the rate dH over dt when H is equal to 20 centimeters. Now, to start with our solution, we're going to begin with the general formula for the volume. It can be the formula volume equal to the cross-sectional area, or the base cross-sectional area times the height, or the volume formula, which includes the product of the cross-sectional area times the length of the solid. The area of the base here for the container is not the rectangular base at the bottom of the container, since this will provide complication in finding the volume of the container, because the sides of this container are in trapezoidal shape. Thus, instead of using the volume formula, which is equal to the cross-sectional area times the height, we will be using the volume formula, which is equal to the cross-sectional area times the length of the container, such that the area would be the cross-section of the trapezoid and the length of the container, which is 2 meters. Then, we can now recall the area of the trapezoid, which is the sum of the base times the height all over 2. This formula uses A and B for the base and H for the height. But in calculus, we avoid using A and B since these are commonly used for the constants. Hence, when we assign variables, we normally use the x, y, or h. So here is the complete picture of the container with these new sets of variables and constants. As much as possible, identify all the constants in your figure because this would simplify equation you will use to represent the situation in the problem. Remember that we are looking for the rate at which the water level is changing. Therefore, we are talking of the water inside the container, not the container itself. So we need to represent the dimensions of the water inside the container, where we can get our equation. To complete the volume equation of the water inside the container, for the trapezoidal cross-section, I make use of x for the upper base and 30 centimeters for the bottom base, since whatever level the water is, the bottom of the container would remain 30 centimeters, just like the 2 meters length of the container. So this makes 30 centimeters and 2 meters constants in the problem. So now, to find the volume equation of the water inside the container, we need to change the parameters in terms of x and h. So therefore, the cross-sectional area of the water inside the container is defined by this equation, area equal to h over 2 times the quantity x plus 30. Again, here, h is the water level and x is the upper base of the trapezoidal cross-section of the water inside the tank. Setting up now the volume equation from the general formula, volume equals to the cross-sectional area times the length of the container. The equation now becomes volume equal to the length of the container times the area of the trapezoid, which is h over 2, times the sum of the quantity x and 30. Now, substituting all the possible constants in the equation, like the length of the container, which also serve as the length of the volume of the water inside the container. Then, changing these meter units to centimeters to express all the parameters in the equation in terms of centimeter. Then, the length now would become 200 centimeter. So again, 1 meter is equal to 100 centimeters. That makes 1 or 2 meters equal to 200 centimeters. So this reduces the equation to volume equal to 100 times h times the quantity x plus 30. Now, this volume equation is an equation of three varying quantities: the volume itself, the base x, and the water level h. Now, if you're going to differentiate implicitly both sides of this equation, we would end up with three related rates, such as dv over dt, dh over dt, and dx over dt. Recall that in the problem, dv over dt was identified, and then we are asked to look for dh over dt. But how about dx over dt? It is not mentioned in the problem, right? Well, in that case, we are not going to look for another missing rate, particularly if it is not included in the problem. So, we need to revise the volume equation and express it in terms of volume and height quantities only. To eliminate x in the volume equation, we will consider the trapezoidal cross-section where we find x. Looking at the detailed picture of the trapezoid, the 30 centimeters for the bottom base is being offset to the upper base, and the remaining parts of the upper base are both 15 centimeters. Since we are talking here of isosceles trapezoid. This would give us two similar triangles, triangles ABC and triangle ADE. With triangle ABC as the smaller triangle with legs H and Y, where Y is the variable used to complete the legs of the triangle ABC. And another triangle, ADE, the bigger triangle, with legs 15 and 50. 50 here is the height of the container. Since their corresponding sides are proportional, then by similar triangle method, the equation would start from y over 15, which is the ratio of the adjacent sides between the two triangles. So this pertains to triangle ABC to triangle ADE. So again, the ratio between the adjacent side of triangle ABC to triangle ADE, which is equal to the ratio of the opposite sides of triangle ABC to triangle ADE. So y over 15 equal to h over 50. Simplifying this would give us an equation of y equal to 3 over 10 times h. So an equation of y in terms of x. So we will use this equation to eliminate x later. After finding an equation of y in terms of h, now another equation can be obtained using x to represent the upper base. This is the upper base of the cross-section of the water inside the container. So here we can determine an equation of x in terms of 30 and twice of y. So x now is equal to 2y plus 30. which is the second equation. After that, substituting the equation 1 to the second equation by eliminating y here and expressing the second equation in terms of the height, we obtain now an equation of x equal to 3/5 of h plus 30. So this equation involves an equation of x in terms of h. Now, if you could still recall the derived volume equation, which is equal to 100h times the quantity x plus 30, we are gonna actually express all of this in terms of h using the equation x equal to 3/5 h plus 30. So replacing x in this volume equation into 3/5 h plus 30, this would therefore be equal now to 100h times the sum of the quantity 3/5 h plus 30 plus 30. So this would give us actually 100h times the sum of the quantity 3/5 or quantities 3/5 h plus 60. And so finally, simplifying this equation would now therefore give us the volume equal to 60 h squared plus 6000 h. Differentiating the volume equation now with respect to time would give us dV over dt equal to the sum of the quantities 120h plus 6000 multiplied with dH over dt. So here, we eliminate the possibility of having dx over dt. After taking the derivatives of both sides, we may now substitute the given rate dV over dt, which is negative 2000, and solve for dH over dt at h equal to 20. So the equation now would become negative 2000 equal to 8400 dH over dt. And so dH over dt would now be equal to negative 5 over 21 centimeters, or rather centimeter per minute. So again, the minus sign indicates that the water level is falling at the rate of 5 over 21 centimeter per minute. For the second example, Xavier, who is 6 feet tall, walks away at a rate of 5 feet per second from the light at the top of the 16 feet pole. Determine the rate at which the tip of his shadow is moving when he is 20 feet from the pole. In the problem, the height of the pole and Xavier are given, which are 16 feet and 6 feet respectively. And the rate at which Xavier is walking away from the pole or light is also given. Then, we are asked to find the rate at which the tip of his shadow is moving when he is 20 feet from the pole. Here is the appropriate figure that shows that we can be able to solve this problem using right triangles. In the figure, the distance between the pole and savior is represented by x. So the rate at which he is walking away from the pole can be represented by dx over dt, which is equal to 5 feet per second. Then, we also have variable L, which represents the distance from the pole to the tip of the shadow. In that case, we are looking for dl over dt. Using the figure, we can now determine the equation by similar triangle method. The smaller triangle includes the legs, which are the height of savior, and L minus x. While the bigger triangle includes legs, which are the height of the pole, and L. So, to use similar triangle, we're gonna look for the relationship between the sides of the ratio of the bigger triangle to the smaller triangle. So starting with the ratio between the adjacent sides of the bigger triangle to smaller triangle, we have L over L minus x. Now, this is equal to the ratio between the opposite sides of the bigger triangle to the smaller triangle, which is 16 over 6. So solving for L, this would therefore give us L equal to 8 over 5 of x. So this is now our working equation. Differentiating both sides of the equation with respect to time, so from L equal to 8 over 5x, this is now equivalent to dl over dt equal to 8 over 5 dx over dt. Now, substituting dx over dt, which is equal to 5, we arrive with a value for dl over dt, which is 8 feet per second. So hence, the rate at which the tip of the shadow is moving is 8 feet per second. That ends my video presentation about applications of calculus in everyday life. Hope you like it. Thank you for watching.